My name is Xiaomei Sherry Cho. Let me begin with a thank you, Irfan, for this invitation. Also, I want to say that I don't do anything quantum computing. So I'm just going to take you to use the Squeals and tell you how the Squeals changed the world of cosmology. So just to give you a little bit background, some time ago, I don't want to tell you how long ago, I was sent to Berkeley from University of Houston by Paul True to do my graduate student research work with John Clark. So Paul says he doesn't really make devices, so if I want to do devices in physics, he has a very good friend at Berkeley, and then, on one flight, they sent me over. And as Weissman said yesterday, John shares an obsession with noise. So when I talked to John said, well, why don't you measure the noise of this wholly designed squeeze? And that is called static magnetic fields. So what do I mean by wholly squeeze? So at that time, at Clark Group, we were working on the high temperature superconducting devices. And we used the bicrystals. So you take the substrate with a grand boundary in between, you deposit YBCl on top of it, and then you pattern them. So also at that time, John just told me, Gene Dansko just did a thesis that they talked to John Clem. Apparently, if you apply magnetic field to your films, there is some kind of relationship between this vortex flux pinned at your film and the film width. So there was already a paper published at APL, I believe, at 1997 issue or maybe 6. But I came in on 1998. So John says, well, of course we can do more. So here's my wholly squeeze design. I don't know if you can see or not on the bottom. Let me figure it out. Okay, this red line is my grand boundary. So there's two junctions right there, and the whole washer has been patterned into these holes. And so this is only one of the design. You heard from Fred Wellsted at Clark Group. You never stop with one. Of course, I've been through many, many different designs. And then, of course, we have to measure noise, right? So here I'm showing only for 3 different designs of squeeze. And this vertical is plotted the flux noise in 1 hertz, which everybody knows. And then this is the cooling field. So these devices are cooled at certain magnetic fields. And then we measure noise, or I measure noise, and then plot this. And then so you can see the star is a solid washer. So naturally, once you apply magnetic field, it cools the inner field, flux moves, generates a noise for you. And bottom here are all this type of design or various different type of design. And it really can show us the relationship, the one that I described earlier. So starting from, we call this called bare squeeze. And then John did not stop there. Let's move on to directly coupled magnetometer. Then let's move on to flip-tripped gradiometer. So I did many, many different generation measurements, many, many late night at the Birch Hall. Then John said, one day, I thought I was done. John looked at me and said, Sherry, but no one would use a squeeze in the steady position. I look at him, was like, what do you mean by that? He said, everybody want to move squeeze. So at the end, we built this magnetocardiography system, and you can see this copper mesh, which consists of these 5 channels of high temperature superconductor devices inside, and this is controller on the top, and then people can just lie in there, and then we have the very nice heartbeat come out. So that was my thesis. So then I graduated. And then John says, well, why don't you stay on for half a year? We need someone help to fire our old niobium system from Fred. So I said, okay, that sounds good. I'll stay on for half a year. The first thing I have to do was read this Fred Bible. And you have to find out the deposition part, which is still quite thick. And then you just have to go through every individual details and then try to help people making the niobium films in the lab. So after that, I decided probably it's time to move on to do something else. So I went to do cosmology. At that time, the whole cosmology team just started using superconducting devices, be able to integrate them, so make a big one, a big array, and then they use a squeeze to read out. So naturally, at Berkeley, we have Paul Richards' group with Adrian Lee and Bill Holzapfel. They need a postdoc can do squeeze and fabrication. And again, conversation between John and Paul, I got a job. So I went just move one office to the other, and I was a postdoc at Berkeley as well. So let me tell you what is the transition edge sensors. It is actually a very simple idea. You take a piece of superconducting films, you deposit them on some type of this membrane, and then you make sure this membrane is weakly thermal linked to the T-bath. Now, if you connect this TS to an input coil of the squeeze, and then constant voltage bias this TS at the lower end of your transition, so if you have any energy comes in, you can convert into heat, then it will heat up your TS from this green dot to red dot. So that resulting in this resistance change will result in this current change in the loop. The current change, then you have a flux change in squeeze, and by measuring squeeze, which we all know how to do, then you can measure the response from the TS itself. And because it's constant voltage biased, so the total power is equally just this incoming power plus the bias that you need at this low point, and it is constant. So it makes it very easy to be able to utilize this concept and then make a bigger system. So what does the transition edge really look like? That's actually my biggest field right now at cosmology is I build different type of transition edge sensors for various different applications. And so here I'm just showing you some concepts. I'm not going to talk about them in my talk here. I'm going to focus on the squeeze readout more. But this is some concept that we have. So a TS actually constructed with some type of membrane I told you about, in order to convert whatever energy you want into a heat, you do need some type of design for absorber. Okay, here I'm showing you, for example, you see this one is a mesh design, and that just impedance match to free space wave, and then so you can couple the lights, and then the TS is sitting right here. You notice there's something I call bling, is because for cosmology measurements, we actually want them to be slow, and TS itself it's really fast. So to slow them down, you put extra heat capacity on top of it. And we just call that, because original design, it just looks like a jewelry, so we call them bling. And you can see there's a various different design. This is more the newer design. Instead of directly couple the heat to a TS itself, we actually design some polarization sensitive probes. So allow me to measure the polarization from CMB photons. And I need to convert that polarization into my heat. So at the end, I dump all the microwave into this meander goal, and that can dump the heat on top of this island, and that's a TS would then can sense the temperature change. So this is all I'm going to talk about TS. If you want to know more, I can tell you more. But one thing you should know is there is a Moore's law in the CMB sensitivity. When I started, which is somewhere around here, you see, we just started about 100 to 1,000 detectors at that time. People are already thinking, but it's doable that you just connect one TS to one squeal, like my diagram, and then you have many wires come out. Another thing you should know, the TS is typically cooled down at 500 millikelvin or 150 millikelvin. Your squeeze sits at 4 Kelvin. So if you are doing 1-to-1 ratio, you're talking about a lot of wiring have to connect from your cold stage to room temperature. So people are talking, how can we make it easier? And then that's the squeeze multiplexer coming in. I remember vividly at that time, I also went to see MCG system company in Canada, and they have a 300 channels. And I asked them, do they do multiplexing? They look at me and say, why do we need a multiplexing? 300 channel was easy. So that's at that green line there. So we thought we were doing something may not be useful, but I can tell you how useful it is for nowadays. So at that time, NIST Boulder was the first group came out with the idea is thinking about time switching. So you think about you switch each squeeze, then that you can read out each TS individually. And so that was the idea, which I plotted 2 channels here. So it's switching 2 channels, the data here. So at the same time, I should show you. So state of the art at that time It's for the time division multiplexer, it's about 128 pixel squeal multiplexer. So that's NIST design. And as you can see here, they do column 1, column 2, and then you switch it from row to row. Okay? So at that time, Berkeley decided we need to do something different. And according to John, it was a conversation between Paul Richards and John Clark. Can we do something different? John said yes, and that's the something different here, and that's my postdoc career. So our idea was the squeeze is wideband, so we don't need each TS connected to one squeeze. Why don't we connect each TS to certain type of LC filter, so then we can read out this frequency, we know exactly this TS response is. And then you can team up, of course, many of them, and then just sum it to one square array. Then you do the regular readout. Okay, so we use 100 square arrays, and we get the square arrays from NIST Boulder as well. That's the idea. This is the first implementation for this idea to the field. So the first project I ever worked on is called Apex SZ. It's a telescope at Chile, and it's trying to see, search for the unknown clusters or galaxies at the universe. And so we were wondering how could the whole thing work, and there was no example to copy, and we just have to come up with the idea. And here you can see the wedge. This is our transition edge sensors. We have to then wire bond, and then we ask TRW at that time, I think they changed the name afterwards, to make the niobium inductor for us. And then we just buy the commercial ceramic capacitors and solder them. And then you see these micro D connectors, then we can connect to the 4 Kelvin squeeze, which is next one. And so for square arrays, it needs to be magnetic shielding because we're going to the field. Nothing we can do, you cannot build a house. It has to open to light. So it took us many generations to think, what can we do? We have the cryoperm, and then also we have the niobium foil, and then the square array on top of it. And then for bias resistor, we buy the commercial one as well. We just solder them. And this long pigtail then connected to my TS. So that's the idea. We went on to Chile, installed them. And so this is our first light, 2005, and in Chile. And you can see our detector. This is a few horns that couples the light, and that's that micro D connector that you saw earlier. And that's a filter to cut down, block out the frequency that we don't care. So at the same time, at Berkeley actually has the other project to go to South Pole Telescope. So for South Pole Telescope, slightly bigger, they wanted different frequencies. Same idea, we do the pi wedge style design, but they do a different frequency all around. But you can see the picture, it's almost identical. And then they went on to South Pole on the first light at 2006. After that, I moved on. And so I went to NIST Boulder. I learned more about TDM, I learned more about FDM, and then we're wondering, what can we do better? So at that time, it's close to here, blue. Instead of a few hundred, we're looking at thousands to 10,000 now. With the design we had earlier at Berkeley, only can max 8 detectors using 1 square arrays. You go down to few thousands, gets difficult. So at NIST Boulder at that time, Ken Irvin and Ben Mays worked on this microwave squeal readout. So frequency domain multiplexer, we work at 300 megahertz. But you can only pack so many detectors within that few hundred megahertz. With gigahertz, we can pack more. And we can also utilize everything that quantum computing groups are using, and we can just literally copy that over, and then we can use that. So the idea starts with you have the feline, and that couple, each individual one is LC again, but now you use the IF squeeze, and then your TS is coupled to an IF squeeze. So if there's any signal comes in from TS, IF squeeze will change inductance, and then we load this resonator, and then you can dephase, and then you can measure them. I'm not going to talk more about it because it's still an ongoing project. At Stanford, also 2 years ago, I moved to Stanford and SLAC. We just started catching up again. NIST Boulder, however, already has the lab proven for 128 multiplexer for the gamma ray detectors. So we're working on it. We really try to catch up from Stanford side for the cosmology especially. So another thing I am doing now at SLAC is I'm trying to build a clean room. And that is the main purpose they try to hire me. SLAC see this Morse load increase that we do need a sensitivity to get more detectors. In order to get more detectors, you really need a semi-production line. You cannot just use the student research lab, research clean room anymore. NIST Boulder has some type of lab like that, and that's what I use. So when I came to SLAC, my job, hello, do not close, is to build a clean room, and that's what I would like to do. And this has been going on design, and we just have the new building donated by Stanford University. And so SLAC is looking for money to build my clean room inside this building. So this clean room will purely for superconducting devices. We may accommodate for some semiconductor fab, but it has to be compatible to my superconducting detectors. So on that note, the end of last year, Stanford and SLAC managers told me they are pursuing a quantum initiative and asked me if we can also use this clean room to develop some quantum sensors and amplifiers. So of course I have to say yes. So everybody's eyes on this clean room now. And we really hope that this year we can send it out and then start building it. So let me come back about FDM at Berkeley. That's what I did with John. And as I said, Chile was first one. We deployed 2005 for 320 TSs. And at that time, the max factor, which means how many square array we need per X detectors. So that first one, we can only do 7. And soon after, a year later, we do the factor is 8. Now, what's the impact? So Berkeley has the following project called Polar Bear at Chile. They deployed 2012, and the factor is 12. And you can see EBAX 16, South Pole. It's a South Pole telescope, and they're using my NIST detectors. Berkeley readout factor 16, Polar Bear 2 this year or last year, factor 40. And this year's season, this winter, which means just in November of 2016, SPT3G just installed them, and then the factor is 68. So now you see it really saves a lot of money and energy, the power as well to read out these detectors. So we're talking about 16,000 TSs now. The next stage, I was telling you, we're going to do 500,000 detectors. And FDM is still on horizon. It's a proven technology, and people try to push to see if they can do 120. And the microwave maxing will hopefully, we're trying to do at least 250. So this is some kind of the instrument paper that we try to write at this moment, and hopefully we can submit it to everybody soon. So that's just about the impact on the field. I want to come back to talk a little bit about clock group. And you can see the combined member with Y. So at that time, it was very lucky that I got sent to Berkeley, and I actually never really need to go back to Houston to present anything. But apparently, of course, professors talk, right? Another thing I remember was that if I wanted to go to some conference, John did not have money to send me. I just need a phone call to tell Paul, and Paul would be like, okay, I'll send you there. So it was my happy years, be able to travel with people, to go to various conferences and meet people. And it's also very happy to be able to have the other 2 female friends from the same group. Helen is here today. And we've been friends since, and we've been sharing the rooms when we were graduate students, and it's a friendship that I have. You can also see the diversity from the group. Something I enjoyed a lot, especially when I first came. English wasn't that good, everything wasn't that good, and people was willing to teach you, and not about your language, but it's about to improve it. And often they would tell me, oh, come on, we don't even know how to speak Chinese. And I really appreciate that. And that builds my confidence and then be able to practice more and be able to talk more. So we also travel to different conferences. And this is one of the interesting conferences that organized by Michael Mook, is a former Clock Group member as well. And I noticed from the program, there was most of the people are all Clock Groups. And so we had a Clock Group small reunion right there. So you recognize Robert. Sabu is here as well. Klaus is there, Achim, and so it was just a good time, and we've been traveling so many years together. And then, of course, we go ski trip. So John and Greta were very nice to let me be on the top so we could actually slant it. And I was top there, I was so tired. I said, I need a break. And they said, okay, we'll break. So that's this picture. So, just a bit fact. So a month from today is John's 75th birthday, and yesterday we just learned tomorrow is John's 49th anniversary at Berkeley. And you heard from Dale, John travels a lot. So he actually flew more than 2 million miles from United Airlines alone. So that's only one airline, okay? And last year at the ASC, we celebrate John's in Squeals in 50 years, and that's the picture. So with that, we all know, the Clock Group culture, scientific background, and training people. To me personally, it's really the learning method that everybody's been talking about. Train you to be able to think independently and train you to learn how to do your research right. And I think that's the quality. And also the Clock Group family, it's always a family. I know if I have a question, just a phone call away. I can call people or send an email to people, and I can always ask. And for that, thank John, and thank everybody for your attention, and so that's all I have to say.
Thank you. We have time for questions. There.
Yeah. So Stanford has a microelectronics fabrication facility of itself, and I know that companies rent time there to manufacture devices, usually for prototypes. I don't know if they make 500,000, but what does Slack promise, or what does Slack need that you wouldn't be able to achieve by just running a small production line out of Stanford's campus facility?
It's more about what superconducting devices require. We found out that we could not use Stanford. For example, Stanford niobium system, we could not use it. Niobium film just doesn't come out right. So we have our own deposition systems now. We also found out from Berkeley experiment, when you have the shared facilities, someone could etch magnetic materials in front of you, and then you put your niobium in, your film just came out all crappy. And so that Berkeley at the end, Berkeley Micro Lab at the end, they were willing to log into all the users what they did, but Stanford would not do that. And so I could not really just sacrifice my wafers because of that. And so everything I do at Stanford takes me half day to clean everything before I can do one wafer. It's just a lot of work, yeah.
Hi, could you tell us the difference between these transition edge sensors as compared to MKIDs?
The MK detectors?
Yeah, what are the differences? What are the advantages of one over the other? If you could explain that a bit. Thank you.
So kinetic inductance detectors, which is very similar to what I showed earlier for the microwave readouts, they just literally use, again, superconductivity is changing kinetic inductance. The good thing is if you find the right correct material, it's a one-layer process. You deposit them, you etch them, but you have to be 100% correct. Otherwise, you start seeing the variations, and that will shift the frequencies. For transition edge sensors, we are doing better in optical efficiency. the coupling. And so far, all the MKs in the field could not prove optical efficiency better than 10%. But at TS, we do better than 90%. Having said that, I do have a hybrid project. I have a project we do OMT couple design. Instead of couple to a TS, I'm actually coupling to MKits. So that's my current project at Stanford right now. Yeah.
Do you have other questions? It's hard to see from here. Yeah, there in the front.
What wavelengths are these mainly detecting? You said you were filtering out some wavelengths you weren't interested in.
So for cosmology, people are looking at somewhere between 40 gigahertz to 300 gigahertz. And we have a window because the project that I'm working on is always ground-based. And so the water line, the oxygen line will cause this noise for us. We have to break out the different windows. Just to give you an example, for 150, we literally are talking about 125 gigahertz to 170 gigahertz. And so that's the range that we're looking for. Yeah.
Yeah.
What is the yield of your system? I mean, do they all work in the same way?
For the transition edge sensors, at least for the project I know, for most recent one, from the SPT pole, for example, our success rate in the whole chain, including readout, when to the field is more than 80%. And sometimes it depends also on the background. Some channel, for some weird reason, it works today, it won't work tomorrow, but it will come back again. Yeah.
I think there's another question in the back.
I was wondering if the astrophysicists are satisfied, or if they also want more. So, are the astrophysicists, are the customers, saying, "Great, we have enough," or are they in the community of never needing, or never having enough?
It's a background noise. So basically, it's how. Of course, they want more. That's one thing. But it's how many places can we put the telescopes on the Earth? I mean, you cannot put it just by Berkeley, for example. And so there's only limited places we could put and limited space. So we want more, for sure. 500,000 is just something we thought it may be able to do the science, breakthrough science that we could do. But if we can do more, we would love to. But this is a thing. This is not just about detector or readout. It's also optical design, the telescope, how big it has to be to accommodate these almost 500,000 detectors, right? I mean, you're going to separate them, then you will have a systematic problems between different telescopes. And so we're actually writing a whole big book now and just try to discuss that. And 500,000, it's just something that we came out, we all agree across the whole board, from science people to instrument people, could be done. And the question is, can we then do some breakthrough science? And that's the discussion right now. Yeah.
Thank you very much.